Hello, greetings and salutations. I am so excited about right now. Why? Well, a lot of reasons. Now is a special moment. It's the moment that separates everything that could be from everything that is. It's actually the only time you can ever do anything is right now. And why am I excited about this particular right now? Because right now, you're going to be learning about the electromagnetic spectrum. Right now, could change your life. Am I overselling the value of learning about the electromagnetic spectrum? Perhaps. Let's see. Let's go on with lesson 2 of optics. The electromagnetic spectrum. Bum, bum. What is it? What is our goal today? Today we want to identify and label. You can read. I'm going to tell you in a nutshell. We're going to learn about the electromagnetic spectrum, what it is, and what it tells us about. And what it tells us about is types of light, or really beyond that, types of electromagnetic energy. Some of which we can see, which we call visible light, and some of which we cannot. What do you think we call that? That's right, invisible light. Bonus for those of you who shouted at the computer or phone. Boom. So before we can talk about the electromagnetic spectrum, we have to talk about waves. Now, I'm sure you think you've seen waves crashing on the beach, perhaps in a romantic from here to eternity type scene. Google it if you don't know what I'm talking about. But actually, you know what? You haven't seen waves. You've seen the energy of waves acting on water. So what does that exactly mean? Well, waves are energy. They're disturbances that carry energy without carrying matter. So waves are not things. They act upon things. If you see a wave, what you're actually seeing is energy that's been applied to the water, perhaps by the wind, perhaps by seismic activity, tsunami. So that's what we're talking about. Now, when we talk about a wave, what are we talking about? We really have to break it down. There's 3 parts to a wave. There is wavelength, that's the distance between the waves. That's the inverse of frequency. All right, I threw 2 words at you. One is inverse, which means opposite of. So if something is the inverse of something, it's the opposite of it. If one number goes up, then the other number goes down. So as wavelength increases, frequency decreases. But what's frequency? Bam! Frequency. How often the wave comes. So if you think about wavelength, it's the distance between the crest of each wave. Frequency is how often the wave comes. So it's pretty logical, right? If the wavelength is shorter, the crests of the waves hit faster. If the wavelength is further, the crests of the waves hit slower. Are there any other things we can use to measure a wave? Absolutely. There's one other unit of measure, amplitude. How big the wave is. Not particularly related to frequency or wavelength, nor particularly important in our discussion of light. Moving forward. What is light? Light is a wave. Is light a wave? Well, light can also be a particle. Which is it? I don't know. Is that confounding? Yes. Is it confounding to scientists today? Absolutely. We call that the wave-particle duality of light, but I'm getting a little bit over my skis here. I'm getting a little bit ahead of myself. Let me just talk about the wave model of light. And what is that? Well, what it says is we can understand light as an electromagnetic energy that has a frequency and a wavelength. So the wave model of light, while not being fully perfect for describing everything that light is, because it is literally the light of our lives. And yeah, that's the second time I've used that term, but this time it's really true. Light is the light of our lives. And it is possible to understand it as a wave, or to put it another way, by saying it's a wave, it helps us to understand a few things. So what is visible light? It's light that has a wavelength between 400 and 700 nanometers. It contains all colors. Roy G. Biv, which is not the band that started up after Belle Biv DeVoe broke up. Roy G. Biv It is actually the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Those are the visible lights that we can see, the visible colors of light that we can see. You combine different ones together, you get different colors. And if you combine all of them together, you get white light, such that we see coming from the sun. Is that everything? Like, is that everything when we're talking about light energy, when we're talking about electromagnetic energy? No, because there's the invisible stuff that I promised you before. That's wavelength above and below 700 nanometers. And these wavelengths include X rays, which are very, very low frequency, high energy, high frequency, low energy, low wavelength, high energy, X rays, long, long wavelength, low energy, radio waves, microwaves, all sorts of gamma rays. Pew, pew. All right, I'm doing the ray thing again. But come on, every time I say ray, I should be able to go pew, pew. I believe that's the law. All right, now we're ready to talk about the electromagnetic spectrum. It's a range of frequencies. That's the spectrum part. Whenever you hear a spectrum, what we mean is you have a range. If something exists on a spectrum, it doesn't exist as one thing or another thing, but rather as a range of possibilities. Color absolutely exists on a spectrum. There's red, but there's a lot of different kinds of reds: darker reds, lighter reds, more purpley reds, more orangey reds. You know what I'm talking about if you're into art. That's an example of spectrum that you can picture in your mind right there. So it's a range of frequencies of electromagnetic radiation. It's another way of saying light, and their respective wavelengths and photon energies or frequencies. It's also a cool picture, which I'm going to show you in a bit. But let's talk about some of these words a little bit. Let's break this down. So light is electromagnetic energy. That's the first concept you have to get. So it's a form of energy that's related to electricity and magnetism. Let's just leave it there for a sec as an explanation. Now, here's the interesting thing. So is radiation. Now, if you look back at that definition, you notice that I said radiation and light are the same thing. Light is radiation. Okay, now we can't see radiation. We can't see X-rays, but some animals can see infrared radiation. That means they can see heat, which is pretty cool. We also, if you play video games, can see infrared radiation when we put on our infrared radiation goggles. But remember, that's not real. When we're playing a video game, it's just a bunch of ones turning into a bunch of zeros and turning back into a bunch of ones, depending on which buttons we mash at which times. So, do you think you're ready to see the electromagnetic spectrum in all of its glory? I think you are. That's my art, people! You know, you're probably looking at this beautiful bit of art and you're thinking, who drew this amazing electromagnetic spectrum? Well, it's me. I drew it. I'm really proud of it. Now, if you look at the top, you might notice I took a lot of space for the title. Why did I do that? For no good reason, other than to force me to jam a bunch of stuff at the bottom. But let's review everything we know about the electromagnetic spectrum. So, the little wavy things, they represent waves. Waves with, as you're going from left to right, decreasing wavelength and increasing frequency. So as you can see, as the wave pattern gets more squished together, you're increasing frequency. As the wave pattern gets stretched apart, you're decreasing frequency, increasing wavelength. On the left side of the spectrum, big wavelength energy, radio waves for FM AM radio, microwaves for cooking your food, and I believe also for carrying your cell phone signals, infrared radiation, which is heat. Then we get into the realm of visible light, which I depicted with a rainbow: red, orange, yellow, green, blue, indigo, violet, Roy, G, Biv. Not to be confused with Belle, Biv, DeVoe. That girl is poison. You know the group. You know who I'm talking about. All right, ultraviolet. Not to be confused with ultraviolence, which is really something referenced in Clockwork Orange, a book that's a really interesting book, and I'm way off topic. Let me get back onto topic. Ultraviolet can give you sunburn. You can be burned by ultraviolence too, but let's just stay off of that topic. Sunburn, ultraviolet radiation, comes from the sun. Now, even more powerful radiation, which can even damage you more greatly, are X-rays, where you can see your bones. And then the last is gamma rays. Hulk smash! Now, let me just say this. Gamma radiation doesn't give you superpowers. Watch Chernobyl to see what that's a TV show on HBO about a meltdown of a nuclear power plant in the Ukraine in the 1980s, and people were exposed to massive amounts of radiation. You'll see nobody became a Hulk. Nobody became a man of spiders or anything else like that. You have been lied to by comic books when it comes to radiation. Maybe not other things, but when it comes to that, please don't get your science from a comic book. Please get it here. Please get it here as much as possible. You saw lesson 1. This is lesson 2. I will be right back for lesson 3 in the future. No laser. No, I'm going to do it. Pew, pew. Peace out, y'all. What?